World is event-based. Countless number of situations, actions, events are happening all around us in every millisecond of our lives. It is no different with systems that we all work with. The need to react to these events in real time is crucial these days. Even a few years ago, some standard techniques like running some batch jobs on daily chunks of data was just fine, just good enough. However, the world moved on since then. Everyone wants to have an insight to their platforms immediately. Any lag may become lost opportunity for the business. Sometimes this is quite a challenge, since amount of these events can be significant, especially if we are talking about internet scale companies. Thousands requests, thousands events a second. Good news is that there are a few techniques and tools that can help us engineers to build systems that accommodate such requirement. One of these techniques is stream processing, which we will deep dive into during today's session. We will see some practical examples in area of risk management platform, which is quite close to my heart since, as Paweł introduced me, I'm leading a team working for one of the biggest online groceries in Europe, Tesco, and we are building a system that detects malicious users' behavior. So, before jumping into the topic, let's run some warm-up exercise here. Please raise your hands whoever heard about GDPR or RODO in Polish. Okay, and who hasn't? Okay, impressive. How did you do that? Anyway, tens of annoying forms, regulations, standards, policies. This is how we perceive RODO. But I would argue that it also has some positive side. What we can observe recently, because of all this GDPR hustle, is that companies started to invest more to take platform security and data protection even more seriously. They tend to invest more in the area of security, which is great news. They do it primarily in order not to get fined, because 4% of annual income may be destructive even for the biggest players in the industry. Although there are some different motivations as well, like avoiding reputation loss and further financial loss caused by hacker attacks. Let's rewind time a bit to 16th of January 2019, not that long ago. Troy Hunt, one of the biggest experts in area of software security, web application security, releases his blog post about something that he called collection number 1. The collection apparently contains 773 million records with leaked users' credentials from websites, forums, all across the globe. I would bet that most of us sitting in this room could find their emails in this collection. If you haven't, go to haveibeenpwned.com after the session and check it yourself. Now, imagine we are working for some successful company that is exposing its services for online customers. What we can observe? Well, this is what we can observe. Credential stuffing attack. So, all types of attackers, starting from script kiddies to huge botnet owners, arise. They run their scripts that iterate over the collection and try to log in to different websites of their target with these leaked credentials. Unfortunately, some small percent of their attempts will be successful. Why is that? Because people have this terrible habit of reusing passwords all over the internet. So if it leaks from one website, no matter how secure the password is, your all online identities are at risk. So what you can really observe is that organizations, call centers starts getting reports that customers' goods were stolen. If you are a noble organization, you want to keep your customers happy, you repay for their loss. But it gets management. Management is getting anxious because company is losing money. No one likes that. They want to fight back. And this is a perfect situation for the challenge to be born. So imagine being in a team that is given a task to increase security level of the whole platform. Depending on time and money already spent in area of security, the platform at this moment can be in different shape and state. The worst case scenario, though, is that you may start from something looking like this. And what your management wants is this. So as you can see, plenty of good steps in between. What do you do first? Of course, you gather requirements. After long sessions with business, you decide that your first iteration will be focused around analysis of login attempts. You will analyze to detect attempts coming from new devices for given user, from new locations from given user, detect attempts coming from botnet agents, and brute force attacks. Now let's see how our input looks like. So regarding our login attempt, we would like to know whether it was successful or not, obviously. We would need some mechanism to match subsequent requests coming, for example, from one browser tab together, and this is, for example, it can be called session identifier. So subsequent requests will have the same identifier. We are also interested in time of this operation, user ID, whether we were able to match user's input to what we have in our user's data store or not. Obviously, to facilitate our requirements, we would need to gather some device metadata, location metadata, and network. Okay, so we have gathered our requirements and summarized our input. Before designing the solution, let's first answer the question what stream processing really is. So if I were to summarize it in one sentence, it would be that stream processing is all about making sense of unbounded streams of immutable events. Two keywords here, unbounded, since as soon as you start consuming your login events, they will just never finish. The stream will be always there. The data will always come. So obviously until you decide to close your business. So the stream is unbounded from this perspective. And immutable, since events are all about the past. You cannot change past. We have no time machines. So that's why events also should not be changed. Stream processing, also called as Kappa architecture, has few different nice characteristics. So events are processed as they happen, one by one, in the way that every event matters. Even single event can have multiple derivatives, can trigger different components of your stream processing pipeline to do their job to calculate specific results that you desire. You have nice continuity of the stream as you process events one by one, and compared, for example, to batch processing, where you needed to put some artificial boundaries by time, by amount of records, and here you don't have this issue. You don't need to think what to do with records in two different chunks. And what is really important here, you are moving towards event-driven architecture. So instead of, for example, querying some database, data warehouse for results, and so the results are calculated where the data is, in the data warehouse, for example, here we are moving data towards our processing components. So the flow is kind of inverted. We will see how it works in the example. About the examples, all of them will be based on Kafka streams because this is technology of our choice. There are a few different great solutions in ecosystem of stream processing like Flink, Storm, Spark Streaming, Samza, but most of them require you to set up their own processing clusters. Whereas with Kafka streams, it's just a library. You can put it in your class path in the application that is based on any JVM language, and here you go. You can start doing your stream processing. Nowadays, there is even more fancy way of doing this with KSQL, but we are also using it, but for different purposes. So this has nice implication because you can reuse your CI/CD, your pipelines to deploy your application. It's no different from any other web applications that you might have. Now let's define our input in more Kafka way. So we will have a message that has a key of session ID and two different sections with event section and metadata one. We will start doing this big picture perspective, obviously from consuming login attempts. We will build different stream processors. This for now, let's treat it as a black box that is just doing its magic and output events if it sees that something is coming from a new device to yet another stream. We will do the same for location, so new stream processor, for location recognition that will output data to new location streams. These two streams can then be combined together and join some information from customer contact preference database, for example, which also can be put in Kafka, but it's a story for a different talk. And user notifier component may send out communication to the user with their preferred channel. But stream processor doesn't only need to have one responsibility. So normally people do not teleport themselves, right? If you know how to do it, just let me know. I would be keen to learn. But this is not the case most often. So we may detect some teleport commuters, let's say. So if someone has signed in to our platform 1 hour ago from Poland, and now we observe an attempt coming from Central Asia, it seems that it may be malicious. Obviously, we have Tor users, we have some VPN users, but we will know about this, and we may have different business logic based on this knowledge. Another stream processor that we may build is botnet recognition stream processor, and which, for example, can consume some blacklisted IPs or build its own intelligence that will calculate reputation for given IPs. And if the pattern from this very attempt is matching with what we have on our blacklists, we can emit particular event. Final stream processor in this group, session statistics calculator, which will just match subsequent calls together and, for example, calculate total attempts in given session, total failed attempts, failure ratios, etc. Whatever is needed to detect, for example, brute forces. All of them, these streams, can be then consumed by our yet another final stream processor here that will gather all of this, combine, apply some business rules in which situation we perceive this attempt as malicious, and obviously it will emit particular event, which can be then consumed by some authentication provider that may, for example, terminate the session or redirect someone to the honeypot. It's up to this provider to decide. So this is what we can do only with one single input stream. But there can be more of them. We can add some business actions here, and it will make our platform, our stream processing platform, evolve. It will be more efficient. It also doesn't need to stop here. So normally we can emit events. We can feed this stream processing platform with events coming from our applications, But we also can utilize Kafka Connect that will gather the data from, for example, these data sources and feed our stream processing platform. Same thing on the other end. We can output results that we gathered in our streams to other applications and to some platforms that we need, that needs this data. There are different connectors. These here are just examples. So we may, there are multiple of them built by Confluent and community. Now let's deep dive, after having this big picture, let's deep dive into one of these stream processors, how we can build this. So, stream processor of my choice was device recognition, and we need to build two things here. First, we need to detect whether attempt is coming from the new device or not, and we also need to build some kind of knowledge base of known devices for particular user. Obviously, we start from login attempts. First, what we need to do is to convert our input to the shape that seems like our final output. We do it with use of map operator. So how map operator works, it's just converting one type of message to the other. What we are doing here is just lifting and shifting some properties to different properties on the output side. We are also calculating the hash out of some properties that seems like stable, insensitive to, for example, updates of browser or operating system. We are also switching the key here, which is quite important for further reasoning. So let's now focus on building our knowledge base of known devices. First of all, we would like to perceive the device as known, as trusted, whenever it's coming from successful attempt. So we are filtering out all unsuccessful events. Then we group them by key and aggregate. These white boxes are operators in Kafka streams. And aggregate operator is quite special because it's stateful. It consumes previous aggregate version and current event. So after very first attempt, when we consume very first attempt for given user, our aggregate is empty. So we just append new device, because it obviously will be new, to the aggregate. With subsequent request for given user, when it comes from the new device will be appended to an aggregate already containing one device. And this is how we get our known devices stream. Now let's switch to the second part. So we need to analyze whether current attempt is coming from already known device or not. We will do it using join operator. But what we are joining against, this is known devices table. Here we have stream, and here we have table. So how it works? So there are these two abstractions in stream processing frameworks. First one is a stream, and the other one is a table. So if you consume something as a stream, you are interested in each event independently. Whereas if you consume something as a table, you are saying that you are interested only in the latest value of given aggregate, of given sum, count, etc. Some aggregating function. So in other words, stream is like a changelog, and the table is like a current snapshot of given value for particular key. In our case, if user is coming with 3 subsequent attempts from 3 different devices, it will be 3 separate events. In a table, though, at each moment in time, we'll have only one aggregate version. At the end, it will have all the 3 devices. There is this nice duality between these two because you can easily go from the stream to the table and vice versa. So after join operator, when we have something from this known devices table, we can enrich our object, attempt from device, with something that I called marker, which is known flag. We will just be able to see, to observe whether the device was in the aggregate or not. We can use, for example, the calculated hash for this in order not to compare all the properties, but we can do it based on the hash, for example. The next step, next operator, will be filter not, which will filter out all known devices because we are not interested in them here. Then we switch the key for purpose of further processing, as we saw in this malicious session analyzer, and we output this all to new device attempt stream. You can challenge me here because we are using join operator, and most of us coming from, for example, relational database world, perceive join as a bit expensive operation. So when we are talking about some huge scale here, doing join every time the request comes, it may seem not so efficient. So why we still have it here? Because it works a bit differently in this stream processing world. So in order to understand it, let's first see how the message is published to the topic in Kafka. Kafka topics have partitions. Partition number is kind of unit of parallelism for us. So when producer is sending a message to the topic, to the stream, it applies some hashing algorithm on the key of this message, and the result of this hashing function is pointing us to a particular partition which will keep the data. There is one interesting property that obviously each subsequent message with given key will always land on the same partition. This partition will be then consumed by one of our processing instances. When this processing instance is bootstrapping, it gets assigned some partitions. And there is yet another interesting property of stream processing frameworks. So corresponding partitions from copartition topics, which means that the topics need to have same number of partitions, are consumed by the same processing nodes. So if the event comes to the second topic with the same key, the same algorithm will be used, it will also land on partition number 2. This partition then will be consumed by the same processing node here, and this processing node may store it locally. It's our example with known devices knowledge base, known devices table. So the table will be stored in a state store of this node, which means that when subsequent attempt for given user is coming to the left stream, it obviously flows to partition number 2, from partition number 2 to instance def, and now if we are doing the join, it's just a matter of in-memory lookup. So it's amazingly fast because the data is already there waiting for you. So no remote calls are required. We have achieved this nice feature of data locality, and this is actually a must when you are building systems that has high volume of traffic and you expect low latency. You want to keep the data close to your computation, which is happening on processing node. Fine. So this design, unfortunately, has one flaw. So it may happen that we may observe race condition here. So for example, if login attempts is consumed and processed first by this topology on on below, and it gets appended, successful login attempt gets appended to known devices, and for example, this topology is lagging a bit, or maybe the processing nodes of it are down for a moment, it's catching up, we may find ourselves in the situation when this known devices stream updates our knowledge base before this join happens. So join result will be inaccurate. We will know that device is already known, whereas it's coming to our system for the first time. So how to fix that? In order to fix it, we need to introduce a dependency. I know it sounds wrong, but in this case, it will help. So we will start, the top topology stays the same, but we will start our known devices topology from new device attempt stream, which we built on the top here. So we are doing exactly the same thing because we have all the data to do it. We are filtering, then grouping by the field of user identifier, aggregating, and outputting results to known devices stream. And having this dependency, we eliminated possibility of race condition. Although this design has, maybe it may work in case of known devices use case, but for example, for locations, it may not be perfect. But let's imagine abstract situation that user is logging in from thousands of devices in our platform. And each device metadata that we store may be quite huge object with multiple properties inside. So what we end up with is data skew effect. So some small percentage of our aggregates are significantly larger than majority of them. And this is really difficult to troubleshoot, even to notice on the live system. So how to fix that? How we can approach it? We will need our old friend composite key. So the idea here is to use user ID with device hash as a key instead of user identifier only, and eliminate aggregate. So the platform now, the stream processing pipeline looks like this. We are using the user identifier and device hash, whereas we are doing map operators and join operator. So previously we had only one row in a table for a given user, one version of an aggregate that was constantly updated. But what we are moving towards here is having multiple rows for a given user, and each row represents different device. So now it works a bit differently, but we can eliminate, so this join is just a matter of going to the memory, checking whether we have particular hash in our data store, so which is actually stored locally. Because Kafka Streams is using RocksDB, which is putting the data in native memory, but you can easily implement your own strategy using, for example, persistent storage or even a hash map. So we have eliminated aggregate, which is stateful. That's why we saved some memory. We saved some bandwidth because we are sending smaller aggregates through the network, and we don't have data skew effect now. Okay, let's move to some side notes. First of all, please define your goals clearly when you start building the pipeline, since it helps to keep your schema clean. You don't need to, basically it's better to enrich the schema later rather than strip it out from unused properties. Read the documentation and check default properties, because it hurts if you don't. Consider delayed events and time windowing. So these are really complex topics that would probably need another session like this, but please put some time in consideration what you do with delayed events, because they can happen. It's distributed system. Consider delivery semantics that you will have between your stream processors, at least once, at most once, exactly once. This is all delivery semantics that you can imagine. You get them using Kafka streams and Kafka, so choose wisely what is really important for each use case. Some valuable resources here. Designing Data-Intensive Applications by Martin Kleppmann, really great book. Designing Event-Driven Systems, Ben Stopford, also describing multiple use cases of stream processing. And Confluent.io blog, really great resource of multiple valuable blog posts about stream processing in Kafka. Heading to the summary, if your use case requires high throughput, requires low latency, fairly low latency, and you have multiple inputs that can have multiple derivatives ending up in multiple outputs, you probably should consider using stream processing. It has great scalability, extensibility, because you can easily imagine building new stream processor, which is somewhat apart from your live pipeline, and you can visualize results, you can validate your assumptions, and this is, when you confirm them, you can only then attach this stream to your customer impacting streams. You have great fault tolerance, data durability because of replication, retention, and compaction configuration on topics in Kafka. You are able to do data replays, so you may find it useful when you build new stream processor to have a look into how this would work with historical data that you have. So this is possible here. And as the last final note, please keep the big picture perspective. It is distributed system, so it requires detailed analysis, since as we have observed, we can easily run into some troubles and do our design poorly. Looking on the architecture and our data pipelines from higher perspective can help to optimize your flows. It will also help identifying some common paths and make your work with the stream processing even more efficient. That's it for now. Thank you very much. I would be glad to answer some questions if there are any. Okay, let's see here. Do we have any questions? Okay. React.
And switch to Q&A.
Okay. How do you measure processing latency? So each time you produce a message, whether this is your input stream from your producer application or the downstream stream processor, you should append the time when you actually calculated this result, when you trigger event to be published. This is how you can visualize this in some, InfluxDB, Grafana, or use InfluxDB to store these this time series data, or you can use some tools like Jaeger, for example, which is specifically designed for this purpose. You mentioned you are using KSQL for prototyping or production cases. Okay, so for now we are using it for prototyping only. Our production pipeline is working on applications in Kafka streams. I know that Confluent now pushes quite heavily into, invests heavily in KSQL, but we have not built any stream processor that is working on production, impacting live customers based on KSQL. we are planning to do it. We will probably run some tests, but it's not there yet. Okay. So does stream to table saving the data in table in DB. So stream to table is switching the representation of the stream. So it's actually putting your data in this state store in memory by default, but you can easily override this behavior. You can keep it also in some persistent storage if you need. How to deal with late events? This is a really tricky one. There are multiple techniques. You can obviously, it depends on your use case really. So you should decide whether an event, if it comes late, it may no longer be important for you. So you may omit it, or you may define some time period where you accept these late events. So this is actually up to the use case. And how do you deal with rebalancing, messing with your partition to processing node assignment? So rebalancing happens whenever some stream processors are down and partitions needs to be reassigned to in the cluster among running instances. So in our use case, we didn't really hurt because of long rebalancing. It also depends on the scale, on how large your cluster is, how many partitions do you have, etc. But it may be painful sometimes, but yeah, it all depends on how you organize it. So yeah, maybe you can grab me after the session to discuss more specific use case around this. Cool. I think we are done.
All right.
To table is not operator actually. If you want to convert stream the file. So yes, before to table, obviously you need to apply some, for example, some grouping as we saw, or some aggregating function like aggregate, reduce, count, and this type of operations, and only then you can convert stream to the table. Okay, thanks.
Okay. Thank you.